As we explore our logistic regression models, it's important to step back and ask, how accurate are the results? To this end, we'll discuss some common evaluation metrics. This is a two-part series. In part 1, we'll talk about concepts, and in part 2, we'll talk about our code. To begin, suppose we wish to predict whether or not it rains tomorrow, yes equals 1, no equals 0, based on two predictors. Today's 9 a.m. humidity level on a scale from 0 to 100%, which we'll represent as x1, and the number of hours of bright sunshine today, which we'll represent by x2. Since y is binary, we can model this relationship using a logistic regression model. In short, our model coefficients suggest that higher chances of rain correspond to higher humidity and less sunshine, and this is consistent with the plot here. Now, suppose today has 80% humidity and 10.1 hours of sunshine. Under those circumstances, do you think it will rain tomorrow? Well, my guess is no, based on the data points with similar humidity and sunshine levels around this red dot. But more rigorously, we can use our model to calculate the probability of rain and use this to make a prediction. Plugging in 80% humidity and 10.1 hours of sunshine, the log odds of rain is roughly negative 2.09. Thus, the odds of rain are roughly 0.124, and the probability of rain is roughly 0.11. That is, there's only an 11% chance of rain tomorrow. So if I had to turn this into a binary yes-no prediction of rain, I would say no. I made this prediction based on a simple rule. If the probability of rain is at least 50%, I'll predict rain. Otherwise, I'll predict no rain. Our data on the weather conditions at left and our probability calculations and binary prediction of rain at right are summarized here. And if we look at the actual rain outcome in the dataset, it turns out that our prediction was correct. It did not rain. But, of course, our predictions won't always be correct. Consider the first 6 data points. Pause your video and ask yourself how many of these predictions ended up being correct. Well, it turns out that there are 3 correct predictions, in addition to the first, which we already discussed. On the 3rd day, we correctly predicted that it would rain. This is called a true positive. We predicted rain would be positive, yes, rain, and the result was truly positive. And on the 4th day, we correctly predicted that it wouldn't rain, and this is called a true negative. But we also made some mistakes. On the 2nd day, we incorrectly predicted that it would rain, but it didn't. This is called a false positive. We predicted rain would be positive, but our prediction was false or wrong. On the 5th day, we incorrectly predicted that it wouldn't rain, but it did, which is called a false negative. And on the 6th day, we had another false positive. These 6 data points bring up some important questions. In general, how good are the predictions from our logistic regression model? And we can break this big question down into 3 more specific questions. Overall, what percentage of our predictions are correct? And breaking that down even further, we can narrow in to what percentage of rainy days are correctly predicted and what percent of non-rainy days are correctly predicted. A confusion matrix provides some insights. To begin, the total column indicates that our dataset includes data on 4,608 total days. It rained on 1,188 of these days, and it didn't rain on the other 3,420. Just as we did for the 6 example data points earlier, we can examine the predictions for all 4,608 days of data. Let's start with the 1,188 days on which it did actually rain. The model correctly predicted rain on 625 of these days, but incorrectly predicted no rain on the other 563. That is, there are 625 true positives and 563 false negatives. Now, putting these numbers together, we correctly predicted rain on 625 out of 1188 days, or 53% of the time. This metric here has a name: sensitivity or true positive rate. In general, the sensitivity is the probability that our model correctly predicts a positive case to be positive. That is the conditional probability that it predicts y equals 1 if in fact y is actually 1. And as we did here, sensitivity can be calculated by the ratio of true positive predictions to the total number of actually positive cases. We can similarly investigate the 3,420 days on which it didn't actually rain. The model correctly predicted no rain on 3,119 of these days, but incorrectly predicted rain on the other 301. That is, there are 3,119 true negatives and 301 false positives. Putting this together, we correctly predicted no rain on 3,119 out of 3,420 days, or 91% of the time. This metric also has a name, specificity or true negative rate. In general, the specificity is the probability that our model correctly predicts a negative case to be negative. That is, the conditional probability that it predicts y equals 0 if, in fact, y is actually 0. And as we did here, it's calculated by the ratio of true negative predictions to the total number of observed negatives. Finally, we can focus on the accuracy of our logistic regression predictions overall. So across all 4,608 data points, there were 625 true positive and over 3,000 true negatives. In total then, we correctly predicted the rain or no rain status on the sum of these, 625 plus 3,119, or 3,744 out of 4,608 total days. Thus, we have an overall accuracy rate of roughly 81%. In general, accuracy measures the probability that our model correctly predicts y, and is calculated by the total number of cases that are correctly predicted, that is, the true positives and true negatives combined, over the total number of data points in the dataset. In summary, we turned our logistic regression probability calculations into binary yes-no predictions using a simple 50% threshold. If the probability of rain is at least 0.5, we predicted rain, otherwise we predicted no rain. And our evaluation metrics suggest that using this rule, our model has a relatively high overall accuracy of 81%, a high specificity of 91%, meaning it's good at anticipating when it won't rain, but it has a low sensitivity of 53%, meaning it's pretty bad at anticipating when it will rain. So you might be a bit worried about this result, and I agree. This does not seem really good. Basically, our model is not much better than a coin flip when it comes to predicting rain. Now, the consequences of such a low sensitivity might be that we get caught in the rain without an umbrella, without a raincoat, and so on. Mainly, there are consequences for an incorrect prediction. But part of the issue here is not our model, but rather our selection of a 50% threshold. The box plots here illustrate the probability of rain on the y-axis as calculated from the logistic regression model for the days on which it didn't actually rain, the left box plot, and the days on which it did actually rain, the right box plot. And the red line represents our 50% threshold. What I want you to notice here is that nearly half of the box corresponding to the actually rainy days falls under the 50% threshold line. That is, the probability of rain was lower than 50% for almost half of the days on which it ended up raining, leading to false negative predictions on these days. In turn, we have a low sensitivity or a high false negative rate for our model. Luckily, nothing says that we have to use a 50% threshold. Instead, it appears that rainy and non-rainy days are better separated, or we can better distinguish between rainy and non-rainy days using a probability threshold of roughly 0.23. Thus, we could change our rule to this. If the probability of rain is at least 0.23, predict rain. Otherwise, predict no rain. So again, we're basically making it easier to predict rain. Now notice that the majority of the rainy box at right is now appropriately above the threshold, and the majority of the non-rainy box at left is below the threshold. In turn, this changes our predictions, And if our predictions change, then our evaluation metrics change. Specifically, the confusion matrix is different with this threshold than it was using a 0.5 threshold. Stepping back, recall that using a 50% threshold for predictions resulted in a specificity or true negative rate of 91% and a sensitivity or true positive rate of 53%. In contrast, you can and should, for practice, use the confusion matrix on the previous slide to confirm that using a 23% threshold results in a specificity of 75% and a sensitivity of 76%. These numbers illustrate some trade-offs in picking a threshold for logistic regression. Using a 50% threshold was good at predicting when it won't rain, but bad at predicting when it will. That is, it had high specificity but low sensitivity. And again, there are consequences, and here a low sensitivity means you might get wet. By lowering the threshold to 23%, we drastically improved our predictions of rain, but at the cost of lowering our ability to predict when it won't rain. That is, we increased sensitivity but at the cost of lowering specificity. Again, this has a consequence. The consequence here is you might carry an umbrella more than you need to. In general, not just in this example, there's a trade-off between sensitivity and specificity. We have to decide which to prioritize and accordingly set an appropriate threshold. For example, which threshold do you think is better here? Now, there's no concrete answer to this question. Rather, it will depend upon the context of our analysis and the real-life consequences of our prediction errors.